Welcome to this video on advanced vat photopolymerization. We will explore key technologies, including SLA, DLP, and two-photon polymerization, along with the underlying chemical kinetics. This video covers the core modalities of vat photopolymerization and advanced mechanisms like clip and sub-micron 2pp, as well as the chemistry driving these processes. Vat photopolymerization is an additive process where liquid resin is selectively cured by light. It relies on the core triad of light, resin, and motion to achieve precision. Next, we will look at the chemical foundations of photopolymerization. The photopolymerization pathway involves three main stages: initiation, where radicals are generated; propagation, where polymer chains grow; and termination, where growth halts. Photoinitiators drive this process. Type 1 initiators undergo cleavage upon absorbing light, while Type 2 require a co-initiator. Matching their absorption spectra to the light source is critical. Resin formulations consist of oligomers for structural properties, monomers to adjust viscosity, and crosslinkers that dictate stiffness. The initiation rate equation highlights how light intensity and initiator concentration determine the speed at which liquid resin solidifies. Gelation occurs at a critical conversion point. For 3D printing, controlling this process and managing overcure is essential for ensuring robust layer-to-layer adhesion. Oxygen inhibition is a key factor, as it acts as a radical scavenger. While it can cause tacky surfaces, this property is purposefully utilized in technologies like clip. Moving on to part 2, we focus on stereolithography, or SLA, and laser scanning mechanics. SLA uses a UV laser for precise, point-by-point curing. This method offers high precision, though it can be slower than projection methods for larger areas. Galvanometer mirrors and f-theta lenses are vital for SLA optics. They allow the laser to trace patterns accurately, while maintaining focus across the entire build plane. The laser's Gaussian beam profile results in a parabolic or bullet-shaped cure line. Understanding this profile is important for predicting voxel dimensions. Finally, the Jacobs working curve provides the fundamental relationship between optical energy and the depth of the solidified resin in SLA processes. Understanding resin behavior is critical. By measuring cure thickness at various exposure energies, we can generate a working curve to extract penetration depth and critical energy. To minimize stress, SLA uses vector-based paths rather than rasterized images. Strategies like staggered hatching help decouple shrinkage stresses and prevent part curling. Next, we explore part 3, focusing on digital light processing, or DLP, a rapid projection-based manufacturing technique. DLP projects an entire 2D cross-section simultaneously using a digital mask. This allows for constant layer times, regardless of the part's complexity or volume. The heart of DLP is the digital micromirror device. These mirrors toggle at high frequencies, enabling precise control over light exposure for grayscale detail. DLP resolution depends on the mirror array and optics. While powerful, there's always a trade-off between the build area and the resulting pixel size. Uniformity is a challenge in projection systems. Because lenses can cause edge light falloff, software correction is often used to ensure even curing across the build plate. To improve surface quality, DLP systems use sub-pixel smoothing. By controlling the exposure intensity of edge pixels, we can effectively mitigate stair-stepping effects. Moving to part 4, we discuss masked stereolithography, or MSLA, an accessible alternative to laser or projection-based systems. MSLA uses high-resolution LCD panels as dynamic masks. This technology has significantly lowered the barrier to entry for professional-grade resin printing. The LCD stack must be carefully managed. Standard panels require modifications, specifically removing color filters to allow sufficient UV light transmission for curing. To maintain precision, MSLA systems use collimated LED arrays. By ensuring light rays travel parallel, we prevent the light scattering that leads to inaccuracies. When comparing DLP and LCD technologies, each offers different advantages in resolution, scalability, and cost efficiency for various industrial applications. In our final segment, part 5, we examine CLIP, or continuous liquid interface production. CLIP bypasses the traditional layer peel cycle by maintaining a liquid oxygen-inhibited "dead zone", allowing for truly continuous and rapid part growth. CLIP utilizes an oxygen-permeable window made of materials like Teflon AF 2400. This window allows pressurized oxygen to flow into the resin, creating a stable, thin, non-polymerized layer. This dead zone is typically 20 to 30 micrometers thick. Its stability is a precise balance of oxygen diffusion rates and the rate of radical initiation caused by UV exposure. Because CLIP runs continuously, fresh resin must constantly flow into the dead zone. However, viscous drag, described by Stefan Adhesion, limits how fast large cross-sections can be printed. Thermal management is also critical. Photopolymerization is exothermic, and in continuous printing, heat can accumulate, potentially collapsing the dead zone and causing a catastrophic print failure. Next, we move to part 6 to discuss various build configurations and their mechanical implications. Vat systems are categorized by their build direction. Top-down systems submerge the part into a deep vat, while bottom-up systems pull the part from a shallow resin tray. Top-down SLA requires a large volume of resin and a recoating blade to level the surface, which is slow but offers high accuracy and low separation stress. In contrast, bottom-up printing uses a transparent film, which enables smaller volumes but introduces peel forces that stress the part after every cured layer. Engineers mitigate these peel forces using mechanical solutions like vat tilting, lateral sliding, or by using flexible FEP films that peel away as the part lifts. Finally, heating the vat is a common strategy. It lowers resin viscosity to speed up flow and increases monomer mobility, enhancing reaction kinetics. In our final segment, Part 7, we explore the sub-micron regime of two-photon polymerization. Standard systems are diffraction limited. To achieve smaller features, we use high numerical aperture optics and highly absorbing resins to restrict curing to a very small focal volume. Two-photon polymerization, or 2PP, uses intense near-infrared lasers. By absorbing two photons simultaneously, initiation only occurs at the focal point. Since absorption scales with the square of light intensity, 2PP allows for true 3D writing inside the resin volume, effectively removing the need for layer-based construction. This nonlinear process enables extreme spatial confinement, allowing us to create nanometer-scale features, pushing the limits of additive manufacturing.